This lesson on electricity and circuits is part 3, focused on parallel circuit analysis. Make sure you've already viewed and understand part 1 and part 2 of the series on electricity and circuits. Okay, quick review. Remember, in a series circuit, we have one path for the current to flow through all three loads or lamps in this case, or which represent resistances to the flow of current. In a parallel circuit, we have more than one path. We have three paths for the current to flow. The difference is, in a parallel circuit, the voltage of the battery is the same across all three lamps or resistances. And then, remember, we talked about that the flow of electricity depends on the resistance in the circuit based on Ohm's law. Voltage equals current times resistance. So the total resistance in the series circuit then is the sum of the resistances of the three lamps. In the parallel circuit, because you have multiple paths for the current flow, the resistance of the overall circuit is much lower because each resistance in each circuit is less than the total resistance in the series circuit. So the current in each of the three circuits, the current in each one is greater than the current in the total current in the series circuit. Then we looked at how to calculate the total resistance in both a series and parallel circuit. In a series circuit, the total resistance is the sum of the individual resistances, R1 plus R2 plus R3. The current is the same that goes through all three resistances. In the parallel circuit, we have the resistances then are added up differently because each circuit has its own current. So when you calculate the total resistance, then in a parallel circuit, it's 1 over the sum of the reciprocal of the resistances, or 1 over the sum of 1 over R1 plus 1 over R2 plus 1 over R3. Now, remember in part 2, we analyzed a series circuit with a 35-volt battery and 3 resistors connected in series, 2 ohm, 7 ohm, and 5 ohm. We found that the total resistance is equal to the sum of R1 plus R2 plus R3, which was then the 14 ohms, which really comes from the 2 ohms plus the 7 ohms plus 5 ohms. Now, from that, we then learned that using the Ohm's law, then that solving for current, that then the current in the circuit would equal the voltage divided by the resistance. Therefore, the total current in this circuit is going to be then the 35 volts divided by the 14 ohms, which is then equal to the 2.5 amps, which then is shown here. The total current in this circuit, the current going through R1, R2, and R3 is 2.5 amps. Again, using Ohm's law, the voltage then, V1, is going to equal then the current times the resistance. So 2.5 amps, that's going to equal then the 2.5 amps times the resistance, which is 2 ohms. which is 5 volts. The voltage across R2 is going to be then 2.5 amps times R2, which is 7 ohms. And then the voltage across R3 is going to be, again, the 2.5 amps times R3, which is 5 ohms. And that's how we got the current and voltages in the series circuit. Okay, now let's look at a parallel circuit using the exact same values that we just used in the series circuit. And we'll compare then the current and voltages in this circuit as in parallel compared to the series. So here we have a parallel circuit with the same 35 volt potential energy source. We have the same resistors, 2 ohms, 7 ohms, and 5 ohms, but now they're connected in parallel, so that each one of these resistors makes up its own circuit. You have the current going through the first resistor, which is I1. Then you have the current going through the second resistor, which is I2. And then you have the current going through the third resistor, which is I3. So now we have 3 different currents. But notice the voltage, the very first question, what is the voltage at each resistor? Well, the voltage, you can see, is the same. The voltage is the same 35 volts at this point. It's the same point here, the same point here, the same point here. So the 35 volts is the same across all 3 resistors. So the first question is easy. In a parallel circuit, the voltage across each resistor, each load, is the same and will be the same as the source voltage, which is 35 volts. But what is the current through each resistor? Well, we've got to use, again, Ohm's law. Voltage equals current times resistance. So we then solve for current, so we're going to use current equals then the voltage divided by the resistance. So now we know that in each circuit we have everything we need to know. So in the current in the first circuit, I1 is going to equal then the voltage, 35 volts, divided by the resistance in that first circuit, which is 2 ohms. So the current in that first circuit is going to be 17.5 amps. The current in the second circuit is going to be the same voltage, 35 volts, divided by the resistance in that circuit, which is 7 ohms. So that's going to be a total of 5 amps. The current in the third circuit is going to be the same voltage, 35 volts, divided by the current resistance in that circuit, which is 5 ohms. And that will be then 7 amps. Now the total current then is just going to be the sum of all 3 of those currents. That will be the total current. So that's going to be then the 17.5 plus the 5 plus the 7. So that says what we have. We have 29.5 amps total. Okay, now let's look at the parallel circuit again, and let's calculate the total current in the circuit using the total resistance this time, rather than getting the individual currents in each of the 3 circuits and adding them together. So to do that, we're going to have to use then the formula to calculate the total resistance, which is shown here, which is, remember, it's 1 over the sum of the reciprocal of each of the loads in the parallel circuit. So let's calculate that. That means then that the total resistance R, I'll just call it R sub S, is going to equal 1 divided by the sum of the reciprocals. So that means 1 over 2, the first resistor, plus 1 over 7 ohms, which is the second resistor, plus 1 over 5 ohms, which is the third resistor. Now, when you calculate that using your calculator, then our total, or our sum, is going to equal then 1.186 ohms. Now we have the total resistance. Now notice the total resistance is dramatically less than the 14 ohms that we had in the series circuit. We now have a very low resistance. Notice it's going to be lower than the smallest resistor in any of the parallel resistance values. So in this case, 2 ohms is the smallest resistor, and your parallel total resistance will always be less than the smallest resistor. So in this case, 1.186 ohms. So now what do we do to find the total current in the circuit? Well, we use Ohm's law. Current equals then the voltage divided by the resistance. So in this case, it's going to be still the 35 volts divided by 1.186 ohms. And we see that it is going to be 29.5 amps, which is the same value we found when we calculated it in the previous slide by adding the 3 currents in I1, I2, and I3. We got the same value, 29.5 amps. And this slide just confirms the values. Now, go to Blackboard and do the parallel analysis problems.